Fire, earth, water and air. The four elements of Aristotle and ancient alchemy. And for good reason. Oxygen and water are the quintessences of life itself. And we as a species depend utterly on their abundant availability. And yet, a growing number of chemists these days expend an extraordinary amount of effort to keep both at bay. This is because during our quest for novel structure and reactivity, we come across many compounds which are hydrolytically and oxidatively labile. This problem is particularly endemic, for example, in organometallic chemistry, where it is far from new. Edward Frankland, late last century, was able to manipulate his alkyl zinc compounds, which inflame spontaneously in air. He used an atmosphere of dry carbon dioxide. These days, not much more than a stone's throw from this oasis of fresh air and water, his apostolic successors employ argon and nitrogen as inert atmospheres and can, with very simple techniques and apparatus, manipulate the most sensitive of materials. This is a dual manifold vacuum inert atmosphere system. This arrangement allows us via these three-way taps to supply alternately a vacuum or an inert atmosphere to any reaction flask connected to this outlet tube. The advantages of this will eventually emerge, but first a word or two about the line. The traditional weapon of the infantry has long been the rifle, the Lee and Enfield, the Armalite and the Kalashnikov. This is yours. And as in all good shock troop maneuvers, success in the field with a minimum of risk is ensured only if you keep your equipment clean, well greased and properly maintained. And this applies in particular to the vacuum component of your line. These manifold taps in particular should be checked regularly for signs of streaking in the grease. Any sign of streaking means that you're guaranteed a leak in the system. If the tap is streaked or dirty, the barrel and the key should be separated and both elements completely degreased thoroughly. Now this is best effected by the use of petroleum ether, in which most forms of, in fact both forms of vacuum grease are soluble, with the use of tissue papers and pipe cleaners. First the key, now the barrel. Now when you're satisfied that all traces of the old grease and any foreign material has been completely removed from both, then the key can be re-greased. Now there are two commonly used forms of vacuum grease. This type here is silicone based, and in fact I prefer this for frequently used taps, for example these manifold taps. It has the advantage that the viscosity of the grease does not alter at all during, well, with changes in temperature in the laboratory. Now, the rule of thumb in greasing any joint, and particularly taps, is that only sufficient grease should be applied to ensure that the final joint is completely translucent, i.e. there are no grey ground glass streaks left. So having done that, key can now be reinserted and turned in to ensure that no remaining streaks of grey remain. So the joint is completely translucent. The other type of commonly used grease is hydrocarbon based, and generally has the trade name apiaison. Now, its viscosity does vary with temperature, and in fact we can make use of that. For example, in these much larger vacuum taps, which are not turned very frequently, apiaison is ideal. And it's useful to warm both elements of the tap before applying the grease, because the grease flows much more easily. Process is easier. This grease is orange, in fact, in colour. But again, the rule is the same. Only sufficient grease to ensure a translucent joint and no more. Warm the key again. And now the barrel. And again, same as before, gently squeeze in the tap, eliminate all signs of streaking. And the joint is guaranteed vacuum tight. There are two small points worth making here about grease and about taps in general. Given the choice, or irrespective of your choice, the cardinal rule is never mix the two different kinds of vacuum grease on the same joint or tap. The high silicone components, the high molecular weight silicones, are insoluble in hydrocarbons, and the result is a rather unpleasant thick white paste, but which is certainly not vacuum tight. It's certainly not a vacuum grease. So keep the two well apart, and don't forget which taps have been treated with which. The other point has more to do with taps. High vacuum taps are distinguished by the fact that their keys are hollow, and all good vacuum lines, in fact, have these hollow key taps. At the point of manufacture, the tap and the barrel, the key and the barrel, are matched. They're ground into each other in order to be completely vacuum tight when they're greased. And they're identified by a number, which appears, in fact, baked onto the key here and engraved, unfortunately, on the back of this tap. It's very important, vitally important, when reassembling your line to make sure that the numbers on key and barrel correspond. Well, we have now switched on the pump, as you can probably hear, and it's supplying a vacuum to the entire system, including the manifold. But like all high vacuum systems, it has a liquid nitrogen-cooled vapor trap. In fact, in this case, this system has two. Now, this is mainly to protect the pump oil from volatile materials which may escape into the manifold. They'll be instantaneously condensed at liquid nitrogen temperature. But we often use the vacuum component of these systems to remove excess solvent at low pressure from reaction vessels. And an extra trap, as we have in this particular system, in which this excess solvent can be collected, is an additional convenience. Now, liquid oxygen may be a hazard in this part of the system. Liquid oxygen has a slightly higher boiling point than nitrogen, and so any liquid nitrogen-cooled vessel open to the air will gradually condense oxygen. Liquid oxygen is a pale blue liquid, rather attractive really, but it's also a spectacular oxidizing agent in the presence of organic solvents, as indeed we would expect to encounter here. It is indeed one of the components of the rocket fuel which powers the space shuttle into orbit. And spectacular though this effect may be, we'd prefer to see it outside the chemistry laboratory. Oxygen will not, however, condense, provided a vacuum or even a partial vacuum is applied to the part of the system. In order to avoid any problem with liquid oxygen then, we must only remember to remove the liquid nitrogen trap, liquid nitrogen flask from the trap prior to letting that particular trap down to the atmosphere. as for example in shutting down the system for the day or in removing the trap to dispose of excess collected solvent. There is no danger under these circumstances of the collection of liquid oxygen. In starting it up, the procedure is usually just to apply vacuum first, and then apply the trap at more or less the same time. That noise from the pump is quite characteristic, quite often useful, in fact, a signal that air is being pumped through the pump. Under these circumstances, that's exactly what we were expecting, but under other circumstances, it can be a guide that there is a leak somewhere in the system which should be tackled. While we're on the subject of this end of the pump, it is vital to let the pump end down to air at the end of the day when you're shutting the pump off. Otherwise, the residual vacuum left, for example, in this trap here, will suck the oil from the pump back up the supply line and into the trap. Now, this is generally fairly harmless, but messy. The inert gas component of the line is simpler and generally easy to maintain. The inert gas itself is provided from cylinder. This blue cylinder indicates that we're using argon in this instance. In extremely rigorous conditions, it's sometimes useful to pass the inert gas prior to entry to the manifold through a special column, a scrubbing column, which removes any excess water or oxygen which may be in the system. But generally speaking, for most purposes, it's sufficient only to purge the manifold thoroughly first thing in the morning, say for 5 minutes, with a very brisk stream of argon. This sweeps out any contamination from particularly oxygen, which can permeate, in fact does permeate, these high density plastic components of the line. And most lines have two exhaust outlets. This one here is a paraffin oil outlet, and that allows us to maintain an ambient atmospheric pressure within the manifold and within any reaction vessels attached to the manifold. Alternatively, the manifold can be exhausted through this mercury outlet. And this allows us to supply an overpressure of inert gas of something like 5 to 10 centimeters of mercury, which may, as we shall see, be quite a useful thing to do. It also allows a safety valve. At that particular pressure, none of the taps in the manifold or in reaction vessels are likely to pop out, so it's an overpressure safety valve. You'll notice also that the mercury outlet is quite tall, remarkably tall in fact. It's slightly more than 76 centimeters in height, and this allows it to function also as an under-pressure safety system. That's to say that should a partial vacuum be inadvertently developed in the inert gas manifold, for example, if we are flooding an evacuated reaction vessel with inert gas, should the pressure drop below atmospheric, it will not allow air to enter by a direct suck back. The column of mercury will climb to 76 centimeters and stop at that point. So it prevents us from sucking air directly back into the system. It's also worthwhile noting at this point that it's desirable to keep a constant, if gentle, flow of gas through the manifold at all times, even when no manipulations are being performed. This is because in this system, we hopefully have a partial pressure of oxygen which approaches zero. In other words, this system is a vacuum for oxygen. And oxygen will, if it can, diffuse in through the plastic, through inadequately greased joints, however it can, in fact. But a constant flow of gas through the system will dilute this and sweep it out of the line all the time. Well, now let's see how the line performs by setting up and running a reaction. One familiar to most of you, I dare say. All Grignard reagents, organomagnesium halides, are water sensitive and to a slightly lesser extent oxygen labile. Their preparation and their handling, therefore, is best performed under a dry, inert, i.e. oxygen-free atmosphere. However, there's little point in supplying this facility if the glassware in which we are going to run the reaction has not been thoroughly, adequately dried off first. Now, there are two approaches to drying glassware. The lazy way, in a sense, is to oven dry it. But this has to be done overnight at least, and at temperatures of at least 100 degrees. Water has a tenacious hold on borosilicate glass, and obviously if we're planning that far ahead, our planning procedures have to be pretty good. The slightly more convenient way, and the one we will illustrate here, is to flame dry the glassware under an inert atmosphere. This is particularly appropriate because the magnesium, which is one of the reagents that we use in greenyard preparation, should also be flame dried. So we should have our components at hand. Just enough grease, remember, to make joints translucent, no more. Otherwise, excess grease will be leached out into the reaction vessel itself. Now, all reactions, all manipulations of air or moisture sensitive compounds must be carried out in vessels which have at least two necks, one of which will always have a stopcock. This allows us access to the flask at all times with an ambient inert atmosphere. Now in this case we require also a reflux condenser and a pressure equilibrated dropping funnel. So a 3-neck flask is called for. Reflux condenser first. Now in fact, in this case, the system will be connected to the vacuum line via the top of the reflux condenser. The reasons for this will be explained presently. Now, any solid reagents, usually air-stable ones, plus a magnetic stirrer should be inserted at this stage before greasing the final joint. And this is best done via a powder funnel, should one be available. So we have magnetic stirrer and magnesium turnings. This particular preparation is using a very healthy excess of magnesium metal. And now that that's done, the dropping funnel can be greased and fitted. Again, no need to overdo the greasing. And of course it has to be close to the atmosphere, so